Equations are complicated for various reasons. So, if you talk of solving these equations, the first step is look for simplifications. Okay, so, everything is 3D. So, if you can solve in 2D, that is a step forward. So, if it is steady state, it is a simplification. So, we look for solutions of Navier-Stokes equations at this stage by enforcing as many simplifying conditions as possible. Of course, there is those equations look formidable, at least for most students. The question arises, how much should I remember for the exam? So, I have given you some handouts. I would say you should be able to remember Navier-Stokes equations in Cartesian coordinates 2 dimensions. In 2 dimensions, how many equations will you have? Mass, 2 momentum and 1 mass. Mass and 2 momentum, 3 equations. You should be able to remember Navier-Stokes equations in 2 dimensions, Cartesian coordinates. Yet, I will give you these equations as a part of the question paper. Okay, not just Cartesian, if anything else is required, I will give you the governing equations, not the solutions. You find the solutions. Now, okay, so steady state was like a very important simplification, and you know flow may not be steady all the time. Sometimes it is steady, but it gives you a limiting answer. The second one was dimensionality. So, it could be 2D or 1D, not 3D, because 3D is a lot more difficult for analysis. So, if somebody told you I did aircraft safety analysis using 2 dimensions, you would say, okay, that is good, but I won't travel in that aircraft. You want all real life calculations to be done in 3D. Okay. So, and I mentioned in the previous class that such calculations will require the use of computers, very, very powerful computers. So, anything you can do on a piece of paper will be small and limited, but at least it is a beginning, and that is where we are. Now, an important approximation we made was that the flow is fully developed. So, it was explained in many different ways. You may call it no edge effects or no entry effects. So, this is analogous to a problem we had studied earlier, where we showed a particle moving in a column of liquid under its own weight. So, if you plotted the particle velocity, let us say u p, as a function of let us say the z coordinate, it would start from 0 and then attain a constant value. So, this constant part was called terminal velocity. So, why does it attain a constant value? Because at that stage, see, initially the weight accelerates the particle, but as its velocity increases, the hydrodynamic drag acting on the particle keeps increasing. How rapidly does it increase? For that you have to refer to that CD versus RE curve. Okay, that gives you an idea. For low Reynolds number, we discussed drag is proportional to velocity. For high Reynolds numbers, drag is proportional to square of velocity, right? Drag coefficient is nearly constant. So, drag is proportional to square of velocity. So, for under a balance of forces, acceleration goes to 0 and velocity becomes constant. So, something similar happens to let us say a flow between parallel plates. So, this is the fully developed part where velocity has become constant, acceleration has become 0. So, the left hand side, these are parallel plates and there is flow taking place in between. So, the left hand side is where you have an entry or an edge effect. So, velocities may keep changing with distance here. So, at a given point velocity may change with position. So, we are talking about steady flow between parallel plates. So, as you move in this direction, see, initially there is, let us say, uniform velocity going in, but later you know that velocity attains a parabolic shape because it is 0 at the wall. So, along the axis velocity has increased. So, along the midplane of that channel, it could also be a tube, velocity has increased with distance. So, what kind of acceleration is it? It is called spatial acceleration. Right? Fluid has spatially accelerated, then attains a constant value and then it becomes constant, and this parabolic profile is realized for all downstream locations for flow between parallel plates. So, this is beyond this point you have fully developed flow. So, you may ask how long does it take for the flow to accelerate and attain a constant value. So, that analysis can be carried out only when you look at the full Navier-Stokes equations. So, but certainly if your parallel plates were not to be very long, then the edge effects would prevail almost everywhere. So, you cannot make the fully developed flow approximation if the plates were to be short. But if they are long, then certainly the flow will be fully developed almost everywhere. So, we had discussed problems of flow through a tube, where the length was maybe 100 meters, diameter was 50 mm. So, L by D was very, very large. So, over there you can carry out a fully developed flow approximation and subsequent analysis based on it. So, flow is steady, there is no temporal acceleration, and if it is fully developed, there is no variation in velocity with distance, and therefore, the spatial acceleration is also 0, which is how the Navier-Stokes equations, let us say the x component of the momentum equation goes from writing the full form just once So, already we have one approximation that pressure includes the body force term. So, here time derivative is 0, flow is fully developed. Therefore, this derivative is 0. Now, if you remember, substituting this equation in mass balance will also give you, since del dot u is 0, you get this term equal to 0, but V is 0 at the walls. Therefore, V is 0 everywhere. So, we have the second term V here. In the momentum equation, we have V times the derivative of u with y. So, that V is 0, u x x is 0. So, it reduces to 0 equal to minus pressure gradient plus mu u y y. This is the fully developed version of Navier-Stokes equations for flow between parallel plates, where the acceleration terms have reduced to 0, which means sum of all external forces equal to 0. What are those forces? Those are surface forces as represented by pressure and viscous stresses as represented by, well, tangential stresses as represented by the viscosity term. But there could also be body forces, but they are absorbed in pressure. For a horizontal channel of limited extent, gravity forces will be in the vertical direction and they do not impact flow in the x direction. So, this equation, okay, what about this term? If V is 0 everywhere, you will have a similar momentum equation for the y component, and that will give you the pressure variation in the y direction equal to 0. If that is the case, then P is only a function of x. So, this can be written, this partial derivative of P with x can be written as total derivative. So, we have, let us say, mu u y y equal to dP dx. P is only a function of x. Now, u derivative with x is 0, therefore, it tells you u is only a function of y. So, here u is only a function of y on the left hand side, P is only a function of x. That is possible only if each is a constant. Some unknown constant to be determined, let us call it C1. So, now you can integrate u and get u is a y plus b. Okay, and a and b are to be found from boundary conditions. Let us just for convenience set up y equal to 0 along the mid plane. So, that gives you u at y equal to plus or minus h equal to 0, which is the no slip condition, and that will give you these constants a and b. Okay. So, you can find a and b. So, this solution will be in terms of the pressure gradient and therefore, constant C1. Now, in a given problem, it is more common either flow is given or the pressure drop is given. Usually, flow rate is what is given, or at least you are designing a system for a given flow rate. So, flow between parallel plates is a specified quantity. You are trying to get an answer for a given flow rate. If flow rate is given, what you know in terms, what do you know? You know the average velocity. How much is it? It is just flow rate divided by cross sectional area. So, what you know is u bar, the average value of u. U bar is 1 over 2 h minus h to h So, if u bar is known to you, the solution u is known, a and b are also known, the constants of integration. You can relate C1 to u bar, and instead of showing you all the intermediate steps, what will be the form of the solution? You can see that it is C1 y square over 2 plus a y plus b, that is quadratic. It is 0 at the walls, non-zero in the middle. So, it has to be a maximum at the center, which is a parabolic profile for velocity. So, after evaluating the constant C1 in terms of u bar, you get this velocity distribution, which clearly is 1.5 times u bar along the axis. So, what came in was u bar, and along the axis it kept increasing till it became 1.5 times u bar. Elsewhere it diminished, reaching 0 at the walls. That is the flow evolution inside the gap between parallel plates. So, this is a wall and there is a flow above it, and let us say it is a stationary wall. So, its velocity is 0. So, when you place it in the flow field under continuum conditions, if you look at particles, particles are all bouncing off that wall. Okay. But when you look at it at the continuum scale, the fluid particles are retarded by the wall and they come to rest effectively. When you see it macroscopically, fluid particles come to rest at the surface of the wall. So, the wall impacts the velocity field. So, this is often called the no slip condition. The wall velocity and the fluid velocity next to it, they are continuous, and the fluid, the surface forces fluid velocity to become 0 at the wall. That is no slip. So, u at y equal to 0 equal to 0. So, this is what the wall conveys to the fluid medium. Now, what does the fluid medium convey to the wall? So, you are running and I stop you. So, you have stopped, but what did I have to do? I had to apply some force, right. So, the fluid conveys shear stresses to the wall. So, the wall experiences, in return, it experiences a shear stress. So, if you remember our fluid element, that was a shear stress. So, now this is the wall. So, this is sigma y x at y equal to 0, which is given a symbol tau wall at y, which is at y equal to 0. So, the result of the fluid result of the surface stopping the fluid is shear stress acting on the wall. And then when you integrate this stress over the length of the surface, you will get force acting on it in the flow direction. Similarly, because the wall is adjacent to the fluid medium, there is a pressure distribution acting on it. Okay, now let's look at a fluid interface. So, maybe this is, let us say it could be water, oil, it could be water, air. Let us say water and air, and this flow from left to right. So, let us call this interface y equal to 0. Okay. So, normally the interface, if you have to use a symbol, how many symbols do you have? You do not have too many. So, this I can also be part 1 of something, or, but here I, capital I is interface. Now, let us say the interface is flat and there is flow from left to right. So, it tells you that the normal velocity at the interface. Now, we are trying to write interface boundary conditions. See, you cannot write Navier-Stokes equations for air and water together. You are solving Navier-Stokes in air, you are solving Navier-Stokes in water, and you are blending the two solutions at the interface. So, you have to apply boundary conditions. Okay, that was readily apparent for the solid wall. You did not apply Navier-Stokes for the solid wall, it's only the flowing medium. So, here you have to solve equations. Those system of equations have to be applied once for air, once for water, and apply, that means you blend the two solutions at the interface through interfacial boundary conditions. That is what we are writing out at the moment. So, if the interface is flat, definitely the normal velocity normal to the interface is 0. So, let us write it as v y equal to 0 plus. So, you understand that u and v are x and y components of velocity, v at the interface 0 plus, that means in air or water? In air. So, is 0, and v at y 0 minus is also 0. Now, you have seen water flowing and then with air above, you can't see air moving, with water moving you can see. The interface velocity is not 0, it is moving. But you can write the no slip condition as u y equal to 0 plus is equal to u y equal to 0 minus. Okay. So, this is the no slip condition. Velocity, whether you measure from the water side or the air side, they are equal, and they are, you may think of water dragging air with it. Of course, you also know that if velocities are sufficiently high, if the layer depth is very high, then the interface will tend to form a wave. When it forms a wave, it may also bring some air into it, and you may have bubbling effects. These are all very complex flow phenomena, but there is no reason to believe that Navier-Stokes will not predict those physical aspects of air-water flow. So, but we have not gone that far. We are just talking about a layer of water moving smoothly, gently over a surface. Now, this is a continuity condition. It's, do you know u at y equal to 0 plus? No, you do not know. Similarly, 0 minus, you do not know. So, this is a continuity condition, not a prescription. If you say u equal to 0, that is a prescription, nothing further is required. But because it is one velocity in terms of another velocity, so you have to prescribe one more, and which will be continuity of the shear stress. So, if you think of a fluid element here and you think of another fluid element from below, they will share the interface and the shear stress will be continuous. So, you can write For 0 plus, here it is air and 0 minus is water. So, I am writing mu A and mu water, air and water. The mu's will not cancel off. Huh? So, what is this? This is the shear stress. You remember the expression for sigma y x. So, how much was it? It's mu u y plus v x, but v is 0 at the interface. So, v x this term was 0. So, you are left with mu u y. Okay. So, I think you can, when you do many problems, suddenly you will realize that shear stress at a surface is mu times the derivative of the tangential velocity with respect to the normal coordinate. Okay. Tangential with respect to normal coordinate. So, suppose it is cylindrical coordinate system, it will be the tangential velocity relative to the radial coordinate. So, these are the boundary conditions you can write for an air-water interface in general. But you can simplify it. Of course, if it is air, if it is water oil, you can't simplify any further. But in case of air water or air liquid, air oil, can you think of a simplification? What simplification can you think of? I am talking about the continuity of shear stress condition. Any simplification that is obvious to you? Huh? Why? What is 0? I don't see any 0. These are the, Suppose A times B is 0, then either A is 0 or B is 0, right? I mean, nothing else is possible, unless I have forgotten my mathematics. What is 0 here? Mu A is 0. It's not 0, but it is small compared to mu water. Okay, but velocities are comparable. See, u y equal to 0 plus is equal to u y 0 minus. Velocities are comparable. Gradients, therefore, you expect them to be comparable. But mu A is much smaller than mu W. Therefore, the left hand side term is expected to be very small. So, as a simplification, so if you write mu air much less than mu water, now please look up the tables. I think it is 2 orders smaller. That means if one is 100, the other is 1. 2 orders. 1 order is a factor of 10. If you apply this condition, then for water, the shear stress is 0. So, a surface on which shear stress is 0 is called a free surface. It is free. There are no stresses acting on it. Okay. So, but if it is a solid wall, shear stress is not 0. In fact, it is the highest in the flow field. So, that is not a free surface, it is a bounded surface, constrained surface. But fluid gas interface is free because shear stress at that interface is small. And to a first approximation, we can set it equal to 0. So, now setting it equal to 0 has a big advantage because now you are prescribing the derivative. So, now you do not have to solve a coupled problem, you do not have to solve air and water, you just solve water, okay, like in the flow between parallel plates problem. So, with this approach, we look at the flow over an incline. This was an example. This is flow over an incline at some angle alpha. This is a solid surface. Okay, this is the fluid layer. x and y are aligned with the flow direction, and this is the vertical coordinate z. Now, initially the flow will, like in that particle moving in an oil column, initially that water layer will accelerate and then will be restrained by shear stresses acting on the solid surface, and then sum of all external forces will become 0, and you will have constant the same velocity at every location along the incline. Okay. So, the acceleration terms are 0. So, here let us write zero. So, this term is 0, therefore, V equal to 0 everywhere, because at the wall V is 0. So, integrating this equation will give you V equal to 0 everywhere. Putting it in the pressure equation, it gives you the derivative of P with y equal to 0, but at the free surface pressure is atmospheric, right. When you come just outside the liquid, pressure is atmospheric. So, that gives you P equal to atmospheric everywhere. So, writing the x momentum equation, we will have 0 equal to minus the pressure derivative plus mu u by y. So, why am I showing P tilde here? Because we know here gravity is obviously important. Gravity is what is draining the flow. This P tilde is equal to the fluid pressure minus rho g x sin alpha, but P is P atmospheric everywhere, therefore, minus d P tilde dx is equal to rho g sin alpha, and the governing equation becomes the second derivative is equal to minus 1 over mu rho g sin alpha, which is a constant. It is another constant C 1. So, you can integrate y equal to 0, u equal to 0. So, B is equal to 0, and the second condition is the free surface condition at y equal to delta. Delta is the layer thickness. The free surface. So, 0 is equal to C 1 delta plus A. So, this gives you constant A. So, now you have A in terms of C 1 and you have a solution in terms of C 1. Okay. So, how did we find C 1 in the parallel plate problem? Their flow was specified. Here also you can find C 1 if the flow contained in that liquid layer is known to you. If you know the amount of flow being carried by the liquid layer, then you can relate it to delta. In units of meter square per second. which is volume flow rate per unit dimension normal to the plane of the blackboard. So, this will give you, if Q is known to you, you can relate Q in terms of delta. So, that way you now have a solution. That is also, the solution is also a quadratic. So, what is the shape of the velocity profile in this liquid layer? Let us say this is the solid surface. And this is your liquid layer. So, I am showing the incline in a as a horizontal patch. What is the velocity variation? See, if the derivative of u with y is 0 at the free surface, what can you say about velocity? It is a maximum, right? Not constant. If it is a maximum, derivative is 0. Am I wrong in saying that? It is a maximum at that point and it is 0 at the wall. That is how there is flow taking place. At the wall it is 0. So, this will give you this is the shape of the velocity distribution in the layer. It is a maximum at the surface, 0 at the wall, and it is a quadratic. Okay. This is the only possible shape if it is going to be a quadratic. Why is it a quadratic? It is a solution of that equation. But you can find the shear stress at the wall. So, that would be mu times the derivative of u with y at y equal to 0. That will give you the shear stress acting on the surface in the y direction along the surface, in the x direction along the surface. That is a free surface. That is what you are the one who said or you said mu air times velocity derivative is 0. That is what you said. So, whatever he said I applied to you. It is a free surface, you understood? Yeah. I am using that free surface boundary condition in this example. So, see, if you have internal flow, what is internal flow? All the flow is confined by a solid surface. It could be flow in a tube, flow between parallel plates, flow through a tube whose cross section is a square or a rectangle or an ellipse. You can have tubes of various shapes. So, when it is flow inside, it is called internal flow. Okay, where if it is outside, it is called external flow. Now, internal flow will come in two categories, will fall in two categories. One is when the flow is driven by a pressure gradient, okay, or a pressure difference. Now, relating it to our discussion of the first part of the course, how do you generate that pressure difference? There is a pump somewhere. Okay. The pump is what pressurizes the fluid and then it goes through an element, a fluid element like a tube. Okay. So, if you have a pump somewhere, then you have generated a pressure difference, which in Navier-Stokes equations will show up as a pressure gradient. Okay. And then there is flow. Now, this pressure gradient, you know your previous discussions where we said losses take place in the tube. So, pressure decreases along the length of the tube. So, that means pressure has this variation. So, you do this problem and show that pressure decreases in the direction of flow. Please confirm it. Not for the free surface problem where P was atmospheric, but internal flow between parallel plates, pressure decreases in the flow direction. Let us see if it is self-evident in the solution. Okay, so I did not take the calculation to a point where I showed that this derivative, the derivative of P with x, will it be positive or negative for flow between parallel plates? It will be pressure decreases in the direction of flow for internal flow. Okay, so this is the variation. So pressure gradient is slope is negative. Okay, so pressure decreases in the direction of flow. Of course, you know that if the cross sectional area changes with the x coordinate, then pressure may increase or decrease, but the total energy will decrease. You know that from your previous analysis. Now, flow can also be initiated by setting pressure gradient equal to 0, but by moving one of the surfaces. So, this is our, I may call it by now, it is our favorite example. So, it is Newton's parallel plate experiment, where one of the surfaces is given this motion and a velocity field is set up. Now, what Newton said was that the force per unit area is proportional to capital U over h, that is all he said. But what is the velocity variation? That we can get from Navier-Stokes equation. So, here the pressure gradient is 0, and flow is set up purely by the motion of the top surface. So, we have 0 equal to mu y y, and u equal to 0, y equal to 0, u equal to 0, y equal to h, u equal to capital U, for which you get a solution which is a linear variation. It is like a linear variation. So, in Newton's parallel plate experiment, the velocity variation in the gap is linear. So, now when you have an applied pressure gradient, like in the parallel plate problem, it is often called Poiseuille flow. So, these are names of engineers who studied those special problems. This is the name of a person, Poiseuille. It's an unexpected spelling. Make sure you cross check it with the book. And when it is 0, like in Kuwait flow, this Newton's parallel plate experiment, it is called Kuwait flow. So, in the tutorial you must have done a problem where you have a pressure gradient and you also have one surface moving. It is called a Poiseuille Kuwait or Kuwait Poiseuille flow. See, as a subject matures, the nomenclature and terminology, they just expand. So, there is nothing more to it. I think it is enough if you remember Navier-Stokes equations. Okay. Is the flow fully developed? Is it steady? Is it incompressible? This terminology should be adequate. So, It's a question that frequently arises. Suppose I have a fluid layer and I start moving this surface, the top surface, and the flow is set in motion. Will the flow reach this linear variation? Will it be established immediately? I think everyday experience tells you that it takes some time for the flow to be established. Now, through a steady state analysis, you cannot estimate how much time it is going to take. For that, you have to solve the unsteady form of Navier-Stokes equations. So, so the question is, how long does it take for the flow to be established in the gap between the two surfaces? So, for that you will have to solve the unsteady form, which is I am still dealing with 0 pressure gradient, and then you will have boundary conditions, y equal to 0, u equal to 0, y equal to h, u equal to capital Y. So, these are u equal to capital U, these are for all time t greater than 0, and at time t equal to 0, the fluid is initially stationary. So, u is 0. So, normally boundary conditions are applied for all time t greater than 0 plus, and initial condition is applied for all time t 0 minus. We distinguish between the two, so that at time t equal to 0, that is when the external disturbance is suddenly introduced. That is when the top surface is suddenly set in motion. Okay. So, this is the governing equation. So, by solving this equation, you will have an idea of how long it takes for velocity to reach that linear variation. What kind of an equation is this? What was that? U y y equal to 0. You would call it an ordinary differential equation, right? In comparison, this is a partial differential equation. So, you are in your what, third semester now, most of you. Have you studied methods of solving partial differential equations? Yes, no, I mean, it's a mixed response. I was about to take it as a strong yes. So, I think what let us not get into the method. How many of you know the method of separation of variables for solving partial differential equations? Please raise your hand. Ah, he knows. Okay. So, you have studied the problems of this type. Huh? What is the nature of the solution? Some infinite series and all that. You have done infinite series, you have seen that infinite series solution. Okay. So, I will not expect you to solve PDEs in this course, but that is not going to stop me from giving you the solution next time. Okay. So, we just look at this little question, how long does it take for the flow field to attain steady state? So, I will see many of you tomorrow, right?